So good morning everyone. Now we'll discuss with the reactance relay. Now the trip law for the reactance relay can be obtained by using the following universal torque equation that we have discussed. If we set K2 in that very case, if we set the value of the K2 is equals to 0 and make K1 positive, K2 equals to 0 and make K1 positive, that is cause the current to produce the tripping torque, and make K3 negative, that is it means that cause the directional torque to oppose the tripping, and K4 can be neglected when the relay is on the verge of operation, then in that very case we will get the following equation. If that case that we have considered, we will get the following equation, that is K1 IR square is greater than K3 VR IR cos of theta minus tau, then it will trip, otherwise it will restrain. So it can be, this equation can be simplified by writing it as we will have this one VR. If we simplify this equation, we are getting VR divided by IR cos of theta minus tau less than K1 divided by K3. So as you have seen from the previous module, we have discussed that this VR IR, it is equals to Z sine. So what is there? So Z sine cos of theta minus tau is less than K1 divided by K3. And let us suppose this is magnitude. So let us suppose that if we set the MT of the directional element to be 90 degree, and let us suppose that this K3 by Kn, it would be Xn, then in that very case what we are getting? We are getting the final value as, the final value can be written as, in that very case will be Z sine, the magnitude of the Z sine cos of theta minus 90, tau we have taken 90 degree, is less than Xn, because K1, K3 we have considered as Xn. So this Z sine cos of theta is, you can say it is Z sine sine of theta cos of theta minus 90 is Z sine sine of theta. Finally it is equals to X sine. So what we are getting, the final expression that we are getting, that if X sine is less than, magnitude of X sine is less than Xn, then it will trip, else it will restrain. So we are reaching this final expression. Now what we have observed from that, we have observed that the relay is the sensitive to only the reactive part of the impedance seen, and trips if the reactive part is less than the particular value, that is Xn, and such a relay is known as the reactance relay, because it is sensitive to the reactive part only, and the operating characteristics is a straight line with an intercept on of Xn on the reactance axis, and the operating characteristics is shown here. So on the Rx plane, if you see that it is a straight line, this is a straight line, and with the intercept of Xn, with an intercept of xn, that is distance from here to here, that is xn on the reactance axis. The entire area below this is actually the trip region, and the below it is trip region, and this is the restraint region. So you can see that the entire this area occupied is too large. So the reactance relay, it occupies a very large area. Now how we can implement it? By using the induction cup structure. Now implementation by using the induction cup structure, how it can be implemented. Now in this case you will see that the current through one of the coil is shifted in phase. That is we will have this current coil, and then this is the operating coil, this is the polarizing coil. Now the current through one of the coil is shifted in phase, so that the torque in this case is proportional to torque proportional to I square is produced by the interaction of the fluxes which is created by the two currents. Now the current through the pressure coil is made to flow nearly in phase with the pressure coil voltage, and by connecting a resistance, the value of that resistance is very high, large compared to the pressure coil inductance, and this makes the phase angle of the pressure coil nearly equals to 0 degree, and as a result, when phase angle is 0 degree, then the maximum torque angle is 90 degree, because maximum torque angle is equals to 90 minus phase angle of the pressure coil that we have discussed in the previous modules. So this 4-pole induction cup structure is a very high torque to weight ratio and is a very sensitive measuring unit. So we will discuss that the performance of the reactance relay during the normal load flow. Now we will discuss the performance of the reactance relay during the normal load flow. As you have seen from the diagram, that the relay occupies all the area below xn on the Rx plane. So the impedance seen by the relay during the normal load flow for a double ends fed system, it falls in the trip region of the reactance relay, and whose operating characteristics is shown here, and thus the reactance relay will operate during the normal load flow. So it cannot be used for that. So this is clearly acceptable, and the reactance relay cannot be used for the protection of transmission line, but needs to be supervised from for another relay to prevent the operation on the load. And the question may arise to the readers that to the engineers that why to bother about the relay which cannot even restrain on the load. So the answer lies in the superior performance of the relay in the face of the fault resistance. So we can discuss the superior performance in face of the fault resistance. Now let us suppose now the effect of the arc resistance on the reach of the reactance relay. Now from this figure it is seen that a line section AB being protected using the let us suppose that AB is being protected by using this reactance relay, and that let us suppose that there be fault at the end of the protected line section at the point B with the resistance equals to BC. So BC is equals to fault resistance due to the arc. So it can be seen that the trip of the impedance seen by the relay, that is this is AC, still remains within the trip region, and thus the reach of the reactance relay remains unaffected in spite of the presence of the arc resistances in that very case. So this is only to be expected, as the relay measures only the reactive part of the ratio of voltage and the current. So this is the superior performance in case of the arc during the arc resistance. So the ability of the reactance relay to respond correctly to the presence of the fault resistance is very useful trait, as you have seen, and accounts for the popularity of the relay in spite of the fact that it undesirably trips during the normal load flow. So the reactance relay finds wide application in the fault locators, where the exact location of the fault can be found out. So it finds application in the fault locators where the exact location of the fault can be found out in the presence of the fault resistance. Now we will discuss the directional property exhibited by the reactance relay. As we have already discussed in the previous module, the first quadrant represents the forward fault, whereas the third quadrant represents the reverse fault. Since the trip characteristics of the reactance relay occupies the areas in both these quadrants, so it does not exhibit the directional relay. So a trip is in both these quadrants, first and the third. So you can say that the reactance relay, which is set to protect the line section AB, so is in the forward direction, also responds to the reverse direction for the unlimited distance. So this again is not a desirable feature, and therefore we should use the reactance relay only along with the directional relay or another distance relay having the directional feature, which is also known as the Moore relay. Now, the performance during the power swing. Now, the reactance relay occupies a very large area in the RX plane that it operates even during the normal load flow, and from this figure it is clear that during the power swing the tip of impedance seen phasor approaches the electrical center of the system, and even before this happens, it is already in the trip region of the reactance relay characteristics. Therefore, the reactance relay operates in the power swing as well, which is not a desirable trait. Now we will discuss the Moore relay. Now we will discuss the Moore relay. Now the trip law for the Moore relay using the universal torque equation. Once again, let us consider the universal torque equation. In this case, let us set K1 equals to 0 and K2 is negative. K1 is equals to 0, K2 is negative. That is, make the voltage provide the restraining torque, because negative is for restraining torque, and make K3 as positive and K3 as positive, and K4 is neglected in that very case. So it is neglected. So the following trip law can be obtained in that very case. That is what we are getting: K3 VR, then we will have IR cos of theta minus tau is greater than K2 VR square. So the relay can thus be described as a directional relay with the voltage restraint, because in that very case the voltage in this K2 is negative. Now the final torque equation, after certain simplifications, we are getting this VR by IR, VR divided by IR is less than K3 by K2 cos of theta minus tau. Now, as VR IR, as you have observed, that we have assumed that VR IR is equals to this Z seen. So this VR IR is equals to Z seen, and let us suppose that it is Z seen. So magnitude of Z seen is less than Zn cos of theta minus tau. In this case, this we have assumed as Zn. Then it will trip, otherwise it will restrain. So if Z seen is less than Zn cos of theta minus, then it will trip, otherwise it will restrain, and theta is the phase angle between the voltage and current which is fed to the relay. Now the relay characteristics is given by this diagram. Now this is the relay characteristics. How here we will have in the RX plane it is represented by this one. You will see that ZR should be less than Zn cos of theta minus tau. That is, then it will trip, otherwise it will restrain. The value of the Zn should be less than ZR should be less than Zn cos of theta minus tau, and in this case you will have this OA is Zn and OB is equals to ZR. So the characteristic is like that. So it means that the area covered by it is very small. Now, the implementation using the induction cup structure. Now, this is the implementation, how we have to implement using the induction cup structure. And in this case, it shows the 4-pole induction cup structure. We have the 4-pole in that. The flux due to the operating voltage coil, the flux due to the operating voltage coil interacts with the induced current due to the current coil to produce the operating torque. So the voltage and the current, the flux due to the operating voltage coil interacts with the induced current due to the current coil to produce the operating torque, which is proportional to that is Vi cos of theta minus tau. The restraining torque in this case is produced because of the fluxes created by operating and the polarizing voltage coils. This is the polarizing voltage coil. So the operating and the polarizing voltage coil, the restraining torque is produced because of that. The resistor R in this case is used, and capacitor C in the voltage coil enable the adjustment of MTA, as we have discussed in the previous lecture. Now, the advantage of the 4-pole induction cup structure is its increased sensitivity due to the high torque to weight ratio over the simple induction disc structure. Now, we will discuss the performance of this relay during the normal load flow. Now, it can be seen from this figure what it is observed. It is observed that the impedance seen by the relay, this is the normal load flow line. So impedance seen by the relay during the normal load double and fed system is well outside the trip region of the characteristics. So the this relay is stable during the normal load conditions. So this relay is stable during the normal load conditions. And now, as we have done the analysis for the arc also, so effect of the arc we have also we have to consider. So now we will discuss the effect of arc resistance on the reach of the Moore relay. So effect of arc resistance on reach of this, we are considering this Moore relay. Now from this we will see, let us consider an arcing fault at the point B. Now the fault occurs at the point B, arcing fault towards the end of the protective line section OA. Now let the fault resistance in this case be BC. Now the impedance seen by the relay, considering the fault resistance, just lies on the verge of the trip region. Any fault beyond this point B will cause the relay to restrain, because it will reach the restraint region. So effectively the reach of the relay has come down from OA to OB. So absolute under reach in this case is AB, and the percentage under reach, as we have discussed in the previous that is a simple impedance relay, that is the percentage under reach is AB divided by OA into 100%. So this is the percentage under reach. Now however, if you see, the simple impedance relay also suffers from the under reach due to the fault resistance. Now if we compare the under reach of the two relays for the same fault resistance, then we find the percentage under reach of the Moore relay is slightly more than that of the simple impedance relay. Now as we have considered, now we will discuss the directional relay, which is exhibited, directional property exhibited by the Moore relay. Directional property exhibited by the Moore relay. So from this figure you will see the characteristics of the direction relay on the RX plane. Now in this case you will see that this characteristics is actually a straight line at the 90 degree to the this MTA line. So the directional relay, that is the straight line at a right angle to the MTA line, the straight line can be considered as an infinite circle, because this is the MTA line, so it can be considered as an infinite circle. A Moore relay is a directional relay with a voltage restraint. So the addition of the voltage restraint to the directional relay, it causes the radius to take an finite value and collapse into a circle with a diameter which is equals to Zn. So with a diameter is equals to Zn, it is like that. So the Moore relay very much possesses the directional property which makes it so useful. So this is the directional property which is exhibited by the Moore relay, that it will trip only in one direction. Now the performance during the power swing. Now the Moore relay occupies a much smaller area in the RX plane, as you have seen. To that extent it is less immune to power swing. However, when the swing is very large, the impedance seen enters into a circle, and then you can say that the relay trips. Special relays known as blinders can be used to prevent the operation during the power swing. So special relays which are known as the blinders, it can be used to prevent the operation on the power, and this prevent the this operation, maloperation during the power swing. So this is all about the different type of relays. Now let us do some comparison of the different type of the relays. Now in this case you will see that we will have this simple impedance relay. Operating is current and restraining is voltage. Directional property, no. Performance is will restrain on load. It will affect on the fault resistance. It underreaches. Area occupied, it is moderate, and effect on the power, it will maloperates. Now for the reactance relay, the operating quantity is current and the restraining quantity is directional element with MTA of 90 degree. Directional property, no. Performance on load, it will trip. Effect of fault resistance, the reach is unaffected. Area occupied is very large and it will maloperate. Now the Moore relay, directional element is, its operating quantity is tau, then restraining quantity voltage. Directional property, yes. Performance on load, it will restrains. Then effect on the fault resistance, it underreaches more than the simple impedance relay. Area occupied is the smallest in that very case, and the effect on the power swing, it will maloperates, though the effect is less than the simple impedance relay. So this is all about the comparison. So from this what we observe that this the reactance, that it is not possible to use the reactance relay, so that it is not possible to use the reactance relay for the transmission line. So we cannot use it for the transmission line on the standalone basis. It is to be used in conjunction with the directional or the Moore element. The Moore relay is much better. It is much better on most of the counts. One remarkable property of the reactance relay is its immunity to the fault resistance that we have discussed. So that is very important property of the reactance relay. However, it lacks stability on the load and does not have the direction property. Considering the pros and cons, the Moore relay is found to be much better fit for the long lines which are likely to be subjected to the large power swings. So it can be used for the long lines which are likely to be subjected to the frequent power swings, whereas the reactance relay in conjunction with the Moore is preferred for the short line. So this Moore relay, it is used for the long line, and the reactance relay in conjunction with the Moore, it is used for the short lines. So this is about the different type of relays. Thank you very much.